Now you can hear me, even better. Right, let's try all of that again. My favorite definition of AI was one I heard last year when a spokesman from Microsoft visited a special school near where I live in Surrey in the UK to give a talk to a group of autistic teenagers about AI and how wonderful it was going to be for all of their futures. And he started, possibly unwisely, by asking this group of autistic teenagers if any of them could give him a definition of what AI actually was. And one young man put his hand up and said, well, it's a failed attempt to simulate human intelligence with a Turing machine. And the Microsoft person looked at him and said, why do you think it's a failed attempt? And he said, well, for a start, artificial neurons are a gross oversimplification of how neurons actually work in the brain, but also brains don't work like that. They're quantum devices. And have you heard about quantum biology? And on and on and on and on he went. And after about 5 minutes, the Microsoft person concurred that it was indeed a failed attempt to simulate AI with a Turing machine, and added, having spent 5 minutes talking to you, I'm not even sure why I think it's so interesting, which I thought was rather charming. Failed attempt to simulate human intelligence as it may be, AI is undeniably having a bit of a moment. We're all under tremendous pressure to use it, to adopt it in our working practices. And that sort of feels like a bit of an inevitable change. So I think it's incumbent on all of us to maybe take a little bit of a step back and think about how we got here, what that means, and how we might use this new technology in reasonably responsible kinds of ways. When we think about how software develops, most software has essentially developed in parallel with Moore's law. So what I mean by that is, as our hardware has got more capable, so our software has more or less followed suit. And that's been true for AI as it is for other forms of software. If you think back to, I'm going to say Alan Turing, maybe as the start of the field, you could argue it's Ada Lovelace and Charles Babbage, but I'll go with Turing. So that's Second World War, that's physical devices, it's not computers yet, in the sense we would understand them, it's physical hardware. But that's sort of, I would say, the beginnings of the field, and then we basically follow through the models of the 50s and 60s and 70s and 80s and so on, and each time our hardware gets better, our AI models have got more capable as well, right? That's more or less how it's worked. That pattern, by the way, is typically followed by what we call an AI winter, and an AI winter is essentially where we realize that this particular technique is less exciting, less useful than we thought it might be, and we kind of row back from it in some way. Yeah, and that's been more or less the pattern that we've seen over and over again. It remains to be seen whether this new wave of large language models, large transformer models, will follow the same pattern or not. We're not quite sure yet. So the big change that's happened in the last decade is the introduction of large language models and related transformer models. I've dated that to 2012. That's the publication of a paper called Attention is All You Need. Again, you could slightly argue about the date. The technique is older than that, but that's more or less where it starts to see mass adoption. What you need for a large transformer model is you need a large corpus of text if you want text as an output, or if you want video, a large corpus of video, or if you want music, a large corpus of music. And basically what you do is you feed that through a transformer, a training process. You build a large virtual neural network. We use some very primitive kind of behavioral training at the end of that process, something called reinforcement learning with human feedback, to kind of tune the outputs so the outputs look a bit more like the kind of outputs that we want. And at the end of that, we have something which will basically produce things that look like things that it's seen before. I would argue there's absolutely no intelligence there. It's just a statistical model that's producing stuff that we then ascribe meaning to as human beings. It's meaningless content that we ascribe meaning to. Other people might disagree with that. The important thing for the purposes of this talk is these models are huge. And you may have heard Sam Altman talk about the idea of what he calls the AI scaling law. Now, that's not a law of physics, right? It's not an actual law. It's more a law that you use to extract money out of venture capital people and other investors. That's really what it's for. But basically, he would argue that if we just keep making these machines bigger and bigger and bigger, eventually we'll get to what he calls AGI, right? Sort of generalized intelligence. I think that's nonsense personally, but you know, we can't both be right. Doesn't terribly matter for this. The point is, building these things takes a staggering amount of compute, and then running them afterwards takes a staggering amount of compute as well. Now, I first got interested in what was going on because I saw this statement from the International Energy Agency that said that combined electricity use from Amazon, Microsoft, Google, and Meta had more than doubled between 2017 and 2021, rising to around 72 terawatt hours in 2021. And I thought, that's odd, I wonder why. Now, you may think the answer to that's pretty obvious. We've added more compute, and therefore, obviously, we've increased our electricity consumption. That would be a reasonable working assumption. It would also be wrong. So it turned out that when we shifted from having our own computers in our own data centers to essentially the utility computing model, utility computing in the Wardley mapping sense, we also converged on a small number of suppliers. Here in the West, that would be Microsoft, Google, and Amazon for the most part. And Microsoft, Google, and Amazon are incredibly good at running data centers really efficiently. What's more, that's where their profit margin is when they're selling services back to you, right? The more efficient the data center is, the less it costs to run. So even as we were adding compute, we weren't actually increasing our electricity consumption very much at all, which is perhaps surprising. So I thought this was odd, and I wondered why it was. Now, I wear a silly number of hats professionally. I'm a consultant. I'm a sort of former programmer, largely. I still do write a bit of code, but not very much. But I'm also a tech journalist. And so with my tech journalism hat on, I thought, I know what I'll do. I'll go and ask people at Microsoft and Google, because I've got contacts there, and they'll tell me what's going on. So I went and asked them, and what happened when I asked them was they looked slightly awkward and tried to change the subject. And that's always really exciting as a journalist, because that tells you there's a story here and somebody doesn't want me to tell you what it is. And that's kind of fun. That's essentially what journalism is. So I went digging. It took me a while, actually 2 years more or less. But eventually, these companies do produce environmental reports. And Microsoft's environmental report from May of 2024 said that its total carbon emissions have risen by 30% since 2020, primarily due to the construction of data centers to meet its push into AI. Aha. Okay, we have our source here. Here's another one. This is from Google. Their emissions have surged 50% since 2019 and 13% year on year in 2023 alone. Again, that's based on their own reporting. And again, that's down to artificial intelligence. And when we say artificial intelligence here, obviously what we mean is these large language models and other sorts of large transformer models. It's not the whole of AI we're talking about. It's very specifically these big models. Now, that matters because as an industry, we don't make our own electricity, right? We buy it from the grid like everybody else. And in most parts of the world, most of that electricity is made by burning fossil fuels, specifically coal and natural gas. It's not true in Sweden, as it turns out, but it is true in an awful lot of the world. And that matters because when we burn coal and natural gas, we release something called carbon dioxide into the atmosphere. I assume you all know that. Carbon dioxide is a greenhouse gas. So the greenhouse gases are a family of gases. It's things like methane and nitrous oxide and hydrofluorocarbons and those kind of things. What they do is they sit in the atmosphere and they trap heat. So light from the sun can pass through them in one direction, bounces off the Earth, can't pass back through them the other direction. The physics is fairly straightforward. Since the Industrial Revolution, we've been increasing the concentration of greenhouse gases in the atmosphere, and what that does is it warms the surface of the planet, right? Again, nothing very complicated about this, probably all very familiar. I should say, by the way, greenhouse gases are actually a good thing. If we didn't have any at all, temperature on planet Earth would be about minus 20 degrees centigrade. That's pretty chilly, and as it turns out, too cold to sustain most life. So the problem isn't greenhouse gases altogether, the problem is increasing the concentrations. That's what this graph shows you. So this is quite a famous graph, it's the Bradley Man hockey stick. It starts in 1000 on the left-hand side there. The blue shaded area is the margin for error. So as you'd expect in 1000, the margin for error is quite wide, and as we get closer to the present day, it narrows, and it's a temperature anomaly graph. So basically, it sort of bundles along, doing nothing very interesting until 1850, which is the Industrial Revolution. Then it starts to climb, and it climbs pretty quickly. Now, I don't know how easy it is to read the vertical left-hand axis from where you're sitting, but it goes from minus 0.8 to plus 0.6. So that graph there represents half a degree of warming. And half a degree of warming doesn't sound like a big deal, and honestly isn't. Half a degree of warming would be fine. You probably know that we've had this goal for a while, this sort of scientific consensus that we want to keep our warming at 1.5 degrees above pre-industrial levels. So that's 1.5 degrees above pre-industrial levels by 2100. And you probably know that's not going to happen. Right, we were 1.5 degrees last year. We'll probably be over 1.5 degrees this year, although we don't know for sure yet. That doesn't actually mean the 1.5 goal is gone because it's an average over several years, because obviously temperatures fluctuate over time. But realistically, we're not going to stop at 1.5 degrees. The best prediction I can give you for where we will end up is somewhere between 2.5 and 3 degrees of warming. It'll be 2.5 if countries do what they say they're going to do. It'll be nearer 3 degrees if we carry on our current trajectory. And that's pretty bad. Right, it's not species ending for us as humans. It's species ending for quite a lot of other species, but probably not for us as humans. But it does mean a lot of humans will die, particularly in poorer countries. It's quite bad. So it's maybe worth saying it's also staggering progress. When I was a teenager, which as you can probably tell was a long time ago now, we were looking at 5 degrees of warming plus. And 5 degrees of warming plus could possibly be species ending for humans. Really bad news. In fact, there were predictions of 6 or 7 degrees. So 2.5 to 3 is massive progress. And I think it's worth emphasizing that because I think it's very easy to get caught in a sort of doom loop when you start thinking about climate change, where you sort of think, well, this is terrible, but there's nothing very much we can do about it, and hopefully I'll be dead and it won't matter, or something, right? That's not the case. We're making staggering progress, and you probably haven't really noticed unless you've been paying attention. It's just sort of happening. What's more, quick show of hands, how many of you are software engineers in the room? That's pretty much everybody. So all of you have a part to play in making this better. And I don't mean by becoming vegans if you're not already, or flying less, or adopting an electric car, or recycling more, or any of those things. Those are all good things to do, but that's not what I mean. What I mean is you can make a huge difference just by doing your jobs better, which is nice, right? We have a part to play. The reason we have a part to play is because as an industry, we're a pretty massive contributor to this problem. Again, I'm going to go back to the International Energy Agency at this point. So they estimate that global data center electricity in 2022, which is the most up-to-date data I could get, was 240 to 340 terawatt hours. So that's about 1 to 1.3% of all global electricity demand. But that number doesn't include networks. And a data center you can't get stuff in and out of is a pretty useless thing. If you add networks in, you slightly more than double the figure. So we go to another 260 to 360 terawatt hours. That's another 1 to 1.5% of all global electricity demand. And that number doesn't include crypto mining. If you put crypto mining in, that's another 110 terawatt hours for possibly the most useless thing we've yet invented to do with a computer. Fine. So what I'm going to do, because those numbers don't make a lot of sense as numbers, so let's pop them on a graph, because graphs help. So here is our industry. I've taken the upper bound of the data centers and networks and added them together. That's 700 terawatt hours. That's about as much as Brazil. Brazil is not the most energy consuming country in the world. That would be China, followed by the United States. It's, I think, about number 6. But for a bit of proportion, what that says is, as an industry, we are like a very large nation state. We're much, much bigger than the UK, where I'm from. There's the UK, 316.9 terawatt hours in the same time period. Just for fun, there's crypto mining, 110 terawatt hours. That's about the same as Norway. Quite similar to Sweden too, as it turns out. Another way to look at that data is that's about as much as aviation. And we tend to think of aviation as being sort of the poster child for terrible for the climate, and we're all supposed to fly less. Well, maybe we need to compute less or something. Fine. There's one other bit about carbon before we get into what we do about this, which is the difference between embodied carbon and direct carbon. So most of what I've been talking about here is direct emissions. Those are the emissions that happen when you power a device. Right? There is another form of carbon, which is the embodied carbon, and that's the carbon that's used to manufacture, transport, and ultimately dispose of a piece of hardware at the end of its lifetime. For your end-user devices, your laptops, your mobile phones, those sorts of things, the embodied carbon absolutely dwarfs the amount of carbon that's used to power it. So I have here an iPhone 13 mini, I think it is. About 83, 84% of all the carbon that will use in its lifetime was used before it got anywhere to me. Therefore, optimizing what happens when it gets to me doesn't make a huge amount of difference. What we want to do instead is we want to extend the lifetime of that hardware for as long as we can. Right? We want to buy them less frequently. 10 years is the heuristic that we're normally given. Quick show of hands, who's got a 10-year-old laptop or a mobile phone? Hands up. Oh, I've actually got like 2 or 3 or 4. Normally when I ask that question, it's like one bloke, and I'm sure he's following me around just so he can put his hand up. But anyway, 3 or 4 of you, that's brilliant. If you're involved in procurement in your companies, then what you want to be doing is buying hardware that's supported longer and putting pressure on your suppliers to extend the lifetime of that hardware further by, keeping it updated, supplying patches and so on. With TPUs, GPUs, that sort of thing, it's a little bit more complicated, and the reason it's a bit more complicated is because they're getting a lot more efficient with each generation. And so although the embodied carbon is substantial, I can't give you a simple heuristic. That's basically what it comes down to. You kind of have to do the maths. Now, obviously, if you're renting these things from Amazon or Google, you can kind of assume they're doing the maths for you. But if you're running your own, you kind of have to do the sums yourself. Part of the reason for that is because more than half of all the electricity in a data center is actually for cooling. And that's why we use water a lot, because water cooling is more efficient than air cooling. It comes with its own problems. Haven't got time to get into that. But the point is that if you have TPUs that run at a lower temperature, then that can make a material difference to how much power we're actually using, because so much of it's in cooling. Does that make sense? I'm seeing nods. Excellent. Good. Right, with all of that in mind, then, the second half of this talk, we'll get into a typical AI life cycle, and what we're going to do is we're going to think about how we might save energy use at each point along that life cycle. So this is a slightly simplified. We've got planning, data collection, training, and deployment and maintenance. Starting with planning, so this is in theory the stuff we do up front before we start building. A really good question to start with is, do I need to do this at all? Bit controversial. I am aware, I've been in this industry 30 years. I know that CV-driven development or resume-driven development is a thing. Most of you said you were software engineers. If you don't have AI on your CV, it's going to get really difficult to get hired when we change the name of software engineering to prompt wrangling or whatever we end up calling our field, right? I completely understand that. I'm also aware that FOMO is a thing that exists for executives. I have been an executive. I can tell you this is true. And your boss, fresh from the golf course, has probably burst into your office and gone, are we AI yet? Whatever the hell that means. And suddenly you're supposed to be AIing stuff, right? Fine, I get it. All I'm saying to you is, think about whether this is the best solution to this particular problem. And also think about, do I need to solve this particular problem at all? I hope when you do problem solving, you come up with more than one solution. That's sort of how it's supposed to work. If you come up with 3 or 4, pick the best one. Typically, if you're using a large language model or something like it, if you're using inferencing, that's going to be the most unpredictable and the most computationally expensive way to solve a given problem. So that problem better be worth solving, and this better be the only way that you can solve it. Otherwise, you're better, I don't know, using some if statements or something, right? Fine. But next question is, do you need to train a model from scratch, or can you use a pre-built one? Training is expensive. It's probably not the most expensive bit, actually. That's probably running in production afterwards. But training is nevertheless expensive and actually quite hard still to do because of the scale as much as anything. So if you can use an existing model and fine-tune it, use some RAG, something like that to get the results that you want, that's obviously better. Model choice also makes a difference, but there is a problem with this, which is you can't get the data to make an informed decision. And the reason for that is kind of back to what I was saying earlier, that people like OpenAI and Google really don't want you to know what's going on, so they won't tell us. So I can tell you that Opt175B, which was Meta's kind of ChatGPT-3 equivalent, used about 1/7 of the carbon to train it as GPT-3 did. But I can't run that comparison for GPT-4 or GPT-5, and the reason is because OpenAI doesn't give me the data and I can't run it myself. So what that means is, if you have a choice, favor an open source model and benchmark it and do some comparisons. There are some tools out there. There's something called ml.leaderboard, which I quite like, but unfortunately it isn't desperately comprehensive. So a lot of the time when you're trying to work this stuff out, you probably have to run some sums yourself, which is a shame, but there we are. Another thing to consider is, can you relax parts of your service level agreement? And if you can, does that allow you to run the workloads in a greener location? And the reason that matters is because we are on a transition. So we're shifting from fossil fuel-based electricity to carbon-free sources of electricity, so renewables and also nuclear. And therefore, where you're running your workloads makes a massive difference. Now, the challenge here always used to be that grids are actually weirdly complicated, and finding out or knowing how green a given bit of electricity is quite hard. You can't sort of look at it and go, how green are you and how were you made? I mean, time was you could. In London, where I lived, you could go to Deptford, which was where the power station was, and just look at it. But now in the UK's grid is connected to the French grid. We have lots of consumer generation, so, microturbines, solar panels on people's roofs, those kind of things. So it's just really hard. But thankfully, there's a company called Electricity Maps across the bridge in Copenhagen, and they've done a lot of this work for us. So what you can do is you can literally go to electricitymaps.com and just look. And that will tell you what the energy mix is at a given point in time in a given country, which is super cool. Because armed with that bit of information, you can say, okay, Sweden is it's almost entirely carbon-free, a mixture of hydro, bit of solar, quite a lot of nuclear. That's very good. So if you can run it locally, obviously you have to factor the network times in, but if you can run it locally here in Sweden, that's going to be a very good thing. That's a very, very simple version of a technique that we call demand shifting. So the basic idea of demand shifting is you shift where or when a workload happens according to the greenness of the power that's available to you. There's a similar technique, which is demand shaping. With demand shaping, we change how an application behaves, either based on user input or alternatively based on, again, the greenness of the electricity that's available. So if you have a washing machine or a dishwasher at home, you're probably familiar with this idea. Your washing machine has an eco button. You press the eco button. It takes longer to wash your clothes, but it uses less power. And the way that it does that is essentially it rotates the drum for longer, uses less water, heats it to a lower temperature. Your dishwasher probably does the same thing, seems to take all day to wash the dishes, but basically what it's doing is soaking them for longer. So you could have a button on your website that says, I don't know, do you want to set fire to the earth and watch it burn? Yes, no, something like that. Your marketing department might want to change the messaging, right? But basically give your users a choice as to whether you use your new shiny AI thing or not. That's one option. Another option is companies like Electricity Maps, there's also another one called Watt Time, W-A-T-T, time, have APIs that you can use that will allow you to identify a window of time where the energy is going to be green. And then what you could do is use your shiny inferencing system at the point when you've got green energy available to you and use your fallback system at a point when the energy is not green. Making sense? Fantastic. Okay, so data collection. We've decided we need our own custom model for some reason, rather than using an off-the-shelf one, which means we need to collect some data. So the next question is, how much data do we actually need to collect? Now, if you're Sam Altman, you believe the answer to that is all of it, literally all of it. All your data belongs to me now. In most companies that I've consulted in, most of the successful projects, for some definitions of successful, that I have seen, all of them in fact, have been what I would class as small language models, not large language models. So what I'm getting at is a lot of the time you might think you have to use an enormous amount of data to do this training, but you probably don't. Another good question to ask is, do I need to collect any data at all? There are staggering numbers of data sets available. Hugging Face had 300,000 when I did this slide, and Kaggle had 430,000. Those are available for free, all of them. And those numbers are probably higher by now, because I wrote this slide 2 days ago. So you might just be able to go and use some existing data set, and that avoids some of the sort of complicated ethical questions that we get into when we collect data as a side effect, which is kind of nice. The next question is, does data collection need to happen on demand? Right? Because if it doesn't, again, we can use our demand shifting stuff. We can bring the data into our central location, if that's the method we're using, at a point when we know we've got a window of green energy available, and do the processing at that point and store it locally until we're ready. Is that making sense? So again, that can work quite well for us. Another really interesting technique is something called, No, we're good, we're good. So that's data collection. Let's shift on to training. Oops, sorry, folks, bear with me 1 second. There we go. So in the same way as with data collection, for any workload that isn't particularly latency sensitive, such as training a machine learning model, it makes sense to do that in a location where we have green energy available, right? That's just, that just makes sense. If we did that for our training, then according to research from University College Dublin, we would reduce our software carbon emissions by between 45 and 99%, just by doing time shifting. So that's quite significant, I think. So it begs the question, why do we not do that? And the answer is because we've set ourselves some sort of arbitrary deadline, or our boss is jumping up and down and going, why are we not AI yet? And we're feeling some pressure. And what I want to get across to you is that's a problem for your marketing people, right? That's solely a problem of communication. It's not an engineering challenge. You could go to your marketing people and say, we need a message for our customers that explains why this is taking a while, and your marketing people could craft you a beautiful message that says something like, I don't know, we think we're working on a solution for this that involves a large language model. We're trying to do it in an environmentally sustainable way, and also we don't want to encourage you to stick glue on your pizza and eat rocks, something like that, right? And most of your customers will probably be fine with this. I'm going to guess most of your customers are not begging you for a large language model right now anyway. So take your time and do it properly. Another interesting technique is federated learning. So what we do with federated learning is usually we have a large foundation model that is central. We send that out to a cohort of devices. We do local training on the cohort of devices, and then we send what are essentially deltas back of the differences. Now, if you introduce some noise into that, differential privacy, that kind of thing, then you end up with quite strong privacy guarantees, and that's actually where federated learning started from. But also, end-user devices don't have the cooling problem that your central data centers do, and as a result of that, this can work out greener. It doesn't always, but it can. There are some other reasons why I think federated learning is really interesting. So here in Europe, we have some smaller data centers which use their waste heat as a byproduct to do something interesting, like heat municipal swimming pools, that kind of idea. Right? In the UK, there's a company called Heater, and they will sell you a little computer that you can attach to the water cylinder in your house. People can run workloads on it, and it heats your hot water as a byproduct, which is kind of fun. The problem with that is those data centers aren't big enough to do large language training, typically, but if we can combine several of them and use federated learning, then suddenly they are. And that's cool because moving heat around is difficult, but if we can make use of it, then we're getting second-order effects that are kind of fun. Any sort of edge-based training can also work out greener in some cases. It's not guaranteed. Typically, it takes longer for the models to converge. So again, this takes a bit longer, but it generally works out better. The other thing to keep in mind here is that size matters. So the reason this is a problem is because we're making ever larger models. So it stands to reason if we could shrink those models back down again, then that's going to work out better for us as well. And that's basically just a compression problem. So there are several techniques that are at various stages of sort of research and production that are interesting here. Pruning, distillation, and quantization are the three main ones. I'm going to whip through these pretty quickly. Distillation is probably the one that is closest to mainstream. It's actually being used quite widely now. The general idea here is you take a large model and a small model. We sometimes call the large model a teacher and the small model a student. I don't terribly like those terms, but those are the terms that get used a certain amount. And basically what you do is you capture good inference runs through the larger model, and you use those to fine-tune the smaller model until the results of the smaller model more or less match the bigger one. Is that making sense? The difficulty there is you have to capture the successful inferencing runs through the large model, and that's not entirely trivial. Amazon Bedrock has some tools that will allow you to do that. There's a sort of emergent category of software that I'm going to call AI middleware, I guess. There isn't really a term for it yet. VMware has some of this stuff with Tanzu, or Broadcom, I guess it is now, has some stuff with some of the Tanzu stuff. I think this is going to happen more and more. Bedrock say that models distilled from Amazon Bedrock can be 500% faster and 75% less expensive than the original models. So that's quite a substantial difference. Quantization, so typically in a model we store the weights and activation values as 32-bit floating point numbers or occasionally 16-bit floating point numbers. If we step those down to like 8-bit, or if the hardware supports it 4-bit or even 3-bit integers, then again that gives us quite a substantial reduction. You lose some precision in that process, so you kind of have to verify that it works, but if you can do it, then it makes a reasonable difference at scale. There is a thing called AQT for TensorFlow operations in JAX. That's a GitHub project from Google that allows you to go and play with this. I have played with it. It's kind of fun and interesting to try. And you can run scenarios for yourselves and see what happens. I mentioned autism at the beginning of the talk, which might have seemed a bit strange. In mammal brains, there is a process that happens called synaptic pruning during development. Basically, what our brains do is they get rid of stuff as our brains develop. There is a theory that in autistic brains, that process either doesn't happen or doesn't work quite right. I spent a lot of time digging into this, and the more I dug into it, the more the evidence for it seemed scant, even though I found the theory kind of compelling. But essentially, the important thing is that as mammal brains develop, we get rid of stuff we don't need. So could we do the same thing with AI? If you think about your insurance company's chatbot, it can probably write Python for you or give you a cheesecake recipe or something. Is that a useful thing for it to be able to do? I mean, it's kind of amusing, but is it useful? Probably not. Right? So if we can get rid of some of that stuff, if we could identify it and get rid of it, again, that would allow us to shrink the model down. And basically, you go from a complex model to a simplified model and a smaller model. All of those techniques can be applied during training, and if you apply them during training, then you end up with a shorter training run. So basically, you get to the end of the training process faster. But they can also be done post-training, which gets you a smaller model in production. We can reasonably assume, and we do have to assume because, again, we can't get the data, but we can reasonably assume that running these things in production uses more energy than training. It sort of stands to reason. You train once, you run them multiple times in production. I can't get data for that, but that seems like a reasonable assumption. So what that means is those techniques, quantization, distillation, and pruning, we can apply them at the end, we can make our model smaller, and that reduces our per inference cost by quite a big deal. There's another technique that I think is super interesting called speculative decoding. This comes out of research from Google. And it's based on an observation, which is that our TPUs and GPUs are hugely parallel pieces of hardware. They can run a lot of things at the same time. But when you stick a prompt into a large language model, that process is a serial process. So when you stick a prompt into a large language model, it responds one token at a time. You can think of a token as being a word or part of a word, right? And that's one token at a time, so we're running a serial operation. So if we could run those operations in parallel, that would be quicker because we're not processor bound, we're memory bound. There's a second thing, which is kind of fun, which is that some words are easier to predict than other words. So we could theoretically have a small model that predicts the easy words and a large model that predicts the more complicated words, and then combine those together at the end. If that's sounding vaguely familiar, that's basically what branch prediction does. Right, in a pipeline CPU. That's essentially how branch prediction works. And what's more, like branch prediction, if the prediction's wrong, that's okay, we throw it away. It still kind of works out in the end. And it turns out speculative decoding does actually work out really well. So by increasing the concurrency, we can run more prompts with less hardware, so that's better environmentally. And from a user perspective, it's better too. And the reason it's better for your users is because we get answers back more quickly. Now, Google put out a statement quite recently saying that the per inference cost of Gemini had fallen by 33 times in the last year. They're not very clear on how they've achieved that, but I'm going to guess speculative decoding is a major part of it. So it's a very interesting, very powerful technique. I've linked there to a research blog, which is quite readable, and links off to some of the more detailed papers if you want to get more of the papers. Beyond that, though, AI is just another compute workload, which means it's a workload like any other, which means that the same sorts of techniques we apply for any workload that we're trying to make green work for AI too. There are basically 4 steps for making all of your workloads green. The first is use the smallest hardware configuration that will actually safely execute the job. We tend to over-provision our hardware as a risk management strategy. And we do that for a couple of reasons, but the main one is actually weirdly historical. It's because procurement used to be unbelievably slow. So when I started in this industry, if I wanted a new server, that process would be measured in months, probably, certainly not weeks. Right? I'd have to fill in a form, I'd have to get that signed by several people, I'd probably have to give them a vial of my blood or promise them my firstborn or something. And eventually someone would buy a server and put the software on it and stick it in a rack. And that whole process took a really long time. And what that meant, we didn't have multi-tenancy either, of course. So every app was running on its own server. And what that meant was someone would come in at some point and say, this new app, how many servers do you want? And you build a simulation, you'd run a load test, you come up with a number like 2, and then you go to procurement and you go, 4, please, just to be on the safe side. And no one ever said, why do you need 4 servers? Your load test says 2, because we were so used to that idea that we just did it. And what's weird is we still do. So I've run audits in a couple of companies where 50% of all of the servers were doing nothing at all. 50%. So we could probably just halve our energy consumption, more or less, by just turning off machines we don't need. The reason for that is, by the way, because an idle server still uses a lot of power, unless it's powered into a low power mode. But if it's just running normally, there's an effect called energy proportionality. And energy proportionality basically means that the static power draw of a server is typically more than 50% of what it uses under load. Right? So that's a huge amount of waste. So use the smallest hardware configuration you can. Auto scaling up and down obviously helps. The next thing is run compute in areas where we have low carbon electricity, like Sweden, and where there are credible plans to make the grid even greener. That, in turn, means use cloud services from cloud providers that have data centers in the places you want to operate in, fairly obviously, but also have tooling that will help you further optimize your workloads. So right now, today, the best in class of the cloud providers is Google. When it comes to actually optimizing workloads, they have tools which actually give you meaningful data that you can take action on. Microsoft's tooling is pretty good. Again, you can do workload optimization with it. Right now, today, November, you can't do that with AWS's tooling. All you can do with AWS's tooling is buy carbon credits. Now, I will say that AWS are aware that that's becoming a problem for them, and they are working to address it. They've done 2 major updates to their customer carbon footprint tool this year. They've changed the methodology to a methodology that's pretty sound and independently audited. We have Scope 3 now. I'm going to assume they'll keep working and it will improve. Let's give them the benefit of the doubt. So I wouldn't move my workloads if I'm on AWS somewhere else, but if I was picking a greenfield, I'd pick Google or Microsoft personally. And then the third thing is optimize the execution time of the jobs to further reduce the carbon footprint. So that's the carbon-aware computing stuff, right? Demand shifting, demand shaping, those things. If you want more on this subject, here are some books. The one on the left-hand side is my own book. It's a free download from the New Stack. I wrote it because people at conferences kept saying, how do I get started? You can read that book in a morning, and it will basically give you sort of Green Software 101. As I say, it's a free download. I've also put another book of mine, Kubernetes at the Edge, on there. That's not really an AI or sustainability book, but it is a book about running workloads with Kubernetes in edge locations, which is relevant if you're thinking about federated learning. Beyond that, the Anne Curry, Sarah Bergman, Sarah Sue book, Building Green Software, is probably the definitive book on this subject. It came out last year, I believe, on O'Reilly. It's very, very good indeed. And I love Hannah Ritchie's book, Not the End of the World. I might have taken a different career path if I'd had that as a teenager, but sadly I didn't because she hadn't written it yet. But it is both a very realistic and a very optimistic take on how we might get ourselves out of this mess. And I love it. With that, I'm going to say thank you very much indeed for listening. If you want a copy of the slide deck, you can scan that QR code there, and that will take you to my website, which has these slides and all of the resources that I've mentioned. I have, I think, about 5 minutes for questions. And I've been Charles Humble. Thank you very much indeed for listening. Yes, sir. Yes.
The first one is you mentioned at the end that this uses as much power as aviation.
It emits as much greenhouse gas as aviation, rather than uses as much power. But yes, Carol.
Which was that in comparison to?
So our industry's greenhouse gas emissions are about the same greenhouse gas levels of emissions as aviation.
And the number for how much power the IT sector uses, does that include AI?
Yes, it does. But it's 2 years ago, because that's the most recent data I can get. So you can reasonably assume that that number is going to climb quite sharply, because we're obviously using more as we're pushing more and more larger and larger generative AI models. I mean, I think there's an economic pressure there. We know that none of these companies can make a profit. So I would assume that at some point, they'll realize this is a silly way to do it, and they'll start using techniques to bring the cost per inference down. But there's no sign of that happening yet because there's so much fake money floating around the system, for want of a better phrase. Does that make sense? So yes, I think the number for our industry will grow. While as interestingly, the number for aviation is fairly flat. Green aviation fuel is problematic for reasons. It's very expensive, mainly. But aviation, I think, is currently doing a better job than IT is, I would argue. Any other questions? It's quite hard to see people under lights. Any more questions? Yes.
Thank you. So essentially what we see now, especially with this area of AI and the Death Star projects of building data centers, which are like terawatt energy hungry, which is basically a couple % of the total US energy production. I do consider that like a Gen 1 technology. And do you have an idea how generation 2 of AI technology would look like? Would it be like a large language model based stack of the methods, or do you predict something different in the future?
Okay, so there's two bits to that question. The first bit is, I think large language models are proving to be useful in some ways, so I think we will continue to use them. But I would argue that we can use some of the techniques I talked about, so some of those compression techniques, pruning and distillation and quantization, and things like speculative decoding to make them run in a much, much more efficient way. But I think the second bit of your question, if I understand you correctly, is, do I think large language models are the end of where we're going with AI? And I don't believe that at all. I actually think that we're already kind of at a commodity point with large language models where they're not going to get a lot better than they currently are. I could be totally wrong, but that's kind of my instinct on it. And I think we will discover new techniques that I can't even begin to imagine yet that are completely different things that work in totally different ways. And it may be that we need completely different hardware even. So it may be that like quantum computing or something like that may end up being part of that answer. But I do think large language models have their uses, and I think, you know, they will be part of our working lives for the next 10, 20, 30 years probably. And therefore, I think it's incumbent on us to find ways to run them that are less damaging. Does that make sense?
Yeah, absolutely.
Yeah, cool.
Thank you.
Okay. How are we on time? I think we're just about, are we? Just about. I've probably got one more. Go on, one more question.
Yeah, you argue that we should use AI models when the electricity is more green in general. But is that a solution, or does that? Because I doubt that the data centers that they use for inference and training the AI models, that they just are not run. So as I see it, they run 24 hours a day. So if we just wait with our workloads, then they will still use the same amount of electricity.
Okay, yes. So that's a perfectly reasonable question. It's half true, half not. Again, if you think of, mostly the way we solve these problems is actually with economic imperatives rather than moral ones. It's not in your interest to be burning money if there isn't demand there. So if we can step the demand down, then it's in my interest to basically use auto-scaling or some other method to scale down and scale back up again. So I think that's one part of the answer. But the other part of the answer is you can put pressure on. Because we use a lot of electricity, if we say we're only going to run in green locations, that encourages governments in those locations to build more green energy there. Does that make sense? And so you end up with a sort of second-order effect that helps. But I mean, you're right. At the moment, bluntly, if you're OpenAI, you're not taking environment seriously in any way, right? You just don't care. There's no getting away from that. This is one of those situations where we as an industry have to take a lead. Regulation, governments aren't going to help us, right? So we have to, I would argue, we need to get ourselves informed and make the best choices that we can given the situation that we find ourselves in. But I would absolutely say if you're only running inferencing in green locations or at green times, then it's going to be in my interest if I'm OpenAI to auto-scale down when the demand isn't there. Is that making sense? Because otherwise, like I say, they're not making money, so at some point that's going to be a problem. Eventually the VCs run out of cash, one hopes. Okay, I think that's time. So thank you all very much indeed for staying. Have some lunch. I will hang around. Thank you.